Hi everyone, welcome to Ray Summit. Congratulations on picking the coolest breakout session. With that, a couple of housekeeping announcements. Please put your phone on silent if you haven't already. Please use the survey in the app so we know where we can improve. With that, let's welcome the team from Latitude AI, Marius, Krishna, and our friend Richard.
Thank you. Hi, folks. I'm Richard, and I'm joined today by Marius and Krishna. We're from Latitude. Latitude was founded in 2023 as a wholly owned subsidiary of Ford Motor Company. We've got about 600 employees across 3 different offices, Palo Alto, Dearborn, and Pittsburgh, which is our headquarters. And then we've also got a test track in Greenville. We support remote work, and of course we're hiring. So if you're interested in Latitude, and specifically also in the work that is presented here, feel free to visit our page. We're focused on developing automated driving technologies for Ford vehicles, and our team in particular is focused on perception machine learning at Latitude. We develop models for 3D object detection in the next generation of Ford vehicles, and our workloads run on Ford's HPC computing center. That's important to note because we have a fixed number of CPUs and GPUs at our disposal, and that means that optimizing our workloads is particularly important for the team's velocity. We're using Ray across our perception ML stack, including dataset generation and offline inference, generating datasets at large scale, and also doing augmentation. We're using it for active learning, selecting the best data to label. For our training data pipeline, which is a multimodal model training with Ray data and Ray train. And then we also use Ray to evaluate models after training. Today we're going to focus on how we optimize our training data pipeline. Overall, we were able to get about a 9x speed up relative to our initial PyTorch DataLoader implementation, and we were able to get about a 3x speed up with a 4x reduction in the number of additional CPUs relative to our initial Ray data implementation. When we first started down this path, we were optimistic that Ray data would be a silver bullet and we could use it as a drop-in replacement to just get a speed up. We saw overall that we did get a speed up, but we also realized that there was a lot of detailed optimization that was required. And we'll go through that in a little bit. Before getting into the details, though, I just want to show a video of the perception performance of one of our models that we train. This shows 3D cuboid detection on a highway scene. You can see vehicles, light poles, signs, etc., classified with high 3D accuracy. One of the problems with training perception models is a data bottleneck. Perception models in particular have multiple synchronized sensors, which include LiDAR, cameras, and radars. This adds up to gigabytes of data per row. And perception models also require pretty rich temporal and spatial metadata. You can think of cuboids, pose, calibrations, etc. And then when you combine this with the fact that the models are lightweight and optimized for inference, what this means is that when you're training on large GPUs like H200s, loading and pre-processing the data becomes the bottleneck and not the model forward-backward pass. I just want to give a brief overview of our data pipeline. We start from Parquet files. These Parquet files are essentially metadata files that indicate what is in the data, what the labels are, and also provide pointers to the sensor data. That's important to note because despite the lack of sensor data, these files are still quite large. They're on the order of terabytes, and we can't fit them entirely in memory. And so even understanding the content of the data with Ray has to be done in a streaming sort of fashion because we can't fit it all in memory. Once we load frames from these files, we load the sensor data. This includes images, LiDAR, and radar. And then once that's done, we augment and transform the data. To the extent possible, we like to save as much of this work to be done on the fly as possible. This gives teams flexibility to investigate how, say, image cropping affects model performance, things like that. And then once we're done with those 3 steps, the pipeline becomes a little bit more standardized. we prefetch to GPU nodes, batch and collate, transfer to GPU memory, and then enter training. So the first half of this pipeline, I would kind of call the data part of the pipeline, and then the second half of the pipeline, starting from prefetching, is more the training loop. And one of the things that we've also seen is that these two parts of the pipeline can be bottlenecks to training. For example, the training data pipeline might actually start out as the bottleneck, you optimize it, and then all of a sudden the training loop is the bottleneck and you have to optimize that. So where we started was that we had an initial PyTorch DataLoader, and we were also using RayTrain. And this setup was delivering limited throughput, even with multi-processing. Our GPUs were underutilized, and the CPUs on the training nodes were fully utilized. We tried increasing the number of workers in our PyTorch DataLoaders. That didn't increase throughput, and our analysis showed that the data pipeline was the bottleneck. One other thing to note here was that we also had some difficulties sharding data sets across the data loaders. If you don't do this exactly right and one of your data loaders runs out of data, you can get stalled ranks, which can cause training to stall as well. Our ML teams solved these problems the best way that they could, which was by increasing parallelism, adding more GPUs, training with large GPU clusters with low GPU utilization. This led to long queue times and frustration across the board. So this is definitely something we needed to improve. And when we were evaluating options, RayData was attractive because it seamlessly allowed us to distribute workloads across heterogeneous clusters. And it also integrated well with PyTorch, basically just a drop-in replacement for a PyTorch DataLoader. To evaluate Ray, we needed an initial implementation. One of the first hurdles we had to get past was that our training setup was sort of a sampling first approach, where our developers were used to being able to specify sampling parameters on the fly. And we always have this mentality of sampling the data set is an experimental parameter. The problem, though, is that Ray data doesn't really give you an opportunity to change the order of data in the pipeline. And so what we had to do is essentially pre-sample the data set. We just wrote out new Parquet files with the data in the order that we wanted to iterate through it. And that let us implement a pipeline like you see on the right, where we used read Parquet, then we used map batches to transform the data, and then finally torch batches to consume the data during training. This initial implementation achieved about a 3x speedup over the PyTorch DataLoader. So at this point, we knew that there was some clear value here. We hadn't seen anything close to this speedup with any of the work that we had tried to do previously. But there was also still a lot of work left to do. One of the ways that we solved this problem was in a brute force sort of way, where we just added a lot of CPUs to the cluster to increase the throughput of data loading. And where we ended up was that we were using about 45 CPUs per GPU, which was unsustainable because we needed those CPUs for other tasks. And then even after moving to Ray and throwing a bunch of CPUs at the problem, the data pipeline was still the bottleneck to training, and the GPU utilization was lower than we wanted. And then something else that I will touch on later is that the pipeline was brittle and error-prone, and we saw somewhat frequent failures. So one of the first things to solve was this sampling problem. Writing out terabytes of pre-sampled files with different weights was tedious. Our ML developers didn't really like doing this. It wasn't something they were familiar with, and it didn't fit with their workflow. So we pivoted to a custom approach here, where at the beginning of training, we would compute sampling statistics once, and then we would use those statistics to generate a Ray data set of row indices that would indicate the order in which the data should be loaded. And then we would proceed with the pipeline as usual, where we would use map batches to transform the data. And so that led to the pipeline that you see here, where we added an additional map batches step to load the rows from the data set of indices. This was much more user-friendly for the team. This was kind of one of the key steps to getting the Ray data pipeline adopted by the team for their day-to-day training work. But there were pain points that still remained. We were seeing frequent out-of-memory problems, some spilling to disk, and then also the training speed was inconsistent. Sometimes the cluster would just go, and then sometimes training would slow down, and we wouldn't know why. So we started digging into the pipeline, and one of the things that we eventually realized is the way that we had architected this pipeline made it somewhat difficult for it to work properly. And so if you look at this, what we did in the first step is we created a data set using from items, and that data set was quite small. It was on the order of megabytes, and it contained many indices essentially. The next step, where we loaded the data from Parquet files, was very fast. It loaded the data in parallel, and it required low concurrency. And the output of this stage was on the order of hundreds of gigabytes. The next step in the pipeline, which was the transformation step, was pretty slow, and so that required high concurrency to get the throughput that we needed. And what we realized was that the row loading would essentially fill up the object store, and the subsequent transformation step couldn't consume the data fast enough. This leads to array data backpressuring the data pipeline, but sometimes it does not do this fast enough and eventually spills to disk. Our instances have fairly small disks, so that could lead to training failing. And then even if we didn't run out of disk, we often saw that this back pressure would just slow down the overall pipeline. So we figured that in order to solve this, we should really just combine these two steps. But we had a problem that the first load row step was pretty fast, but it was memory intensive. And if you combined it with this second step, we just could not get the concurrency that we needed without running out of memory. So I'll turn it over now to Krishna, and he'll talk about the optimization that we did from here.
Right. Thank you, Richard. Hi, everyone. I'm Krishna. I work on training pipelines here at Latitude, and we'll be continuing the presentation from here. So as Richard just mentioned, merging the array data stages was not exactly possible because we were running into ohms. And so when we dug deeper, what we found was the DuckDB-based sampler that we were using that was holding all of Parquet files in memory, and it also leaked memory over time. So switching to a pure arrow-based sampler with explicitly cleaning up any tables that are being generated fixed the issue. And so that actually enabled merging the map batches stages into one. So that had a good number of outcomes. So because we switched out of a DuckDB-based sampler to an arrow-based sampler, that reduced the memory usage for the actor by 50%. And because these stages were merged into one, that also led to a lower object store memory usage because there were no more intermediary objects that were staying alive in between those stages. And because of this lower memory usage, what that allowed us to do was increase the concurrency by like a lot. It also had some other side effects where we could now set like a lower object store limit for the array data set. And that meant that it would free up more resources for other array operations in the cluster. And lastly, because you have these two stages with different concurrency requirements, and these are fused into one, you just have fewer parameters to tune. Like you don't have to worry about one of the stages being having a slow throughput and the other one having a other one being faster. So because of that delicate balance, sometimes you might also see some memory instability. But just merging them into one sort of fixed that issue. And lastly, these pipelines, they were a lot more stable, and the throughput was more consistent. So here are the throughput plots of before and after the change went through. So before the change, you can see the data pipeline takes some time to scale up, and it scales up maybe in the mid of the epoch. But after the change, you can see that the data pipeline scales up almost immediately, and it reaches that steady state speed, and it maintains that through the end. One other thing to notice over here is the data pipeline can actually produce rows faster. Like you can see some spikes where it reaches speeds beyond the steady state speed, but the only reason it doesn't do is because it is being bottlenecked by array data. So with that, actually the bottleneck moves to the training step, So as Richard mentioned, there are two parts, the data pipeline and the training step. So the bottleneck keeps moving, and so we just move towards optimizing the step that is actually slower. So when we profiled the training step, what we found was 40% of CPU time was actually spent on prefetching and collation. So the solution was obvious. We just move the prefetching and collation to a different dedicated prefetch actor, and then transfer these patches from the prefetch actor to the main retrain actor using the object store. Within the retrain actor, we also perform a non-blocking host-to-device copy, so that and we do that in a separate thread, so that doesn't stop the model forward-backward pass. The outcomes from that was more CPU availability for the model forward-backward pass, and so the CPU utilization jumps from 60% to 85%. And with that, the bottleneck moved back to the data pipeline, and then we started to see what else could be done within the data pipeline. So one of the things that the data pipeline does, or it is heavily bottlenecked on file I/O, and one of the main reasons why it is bottlenecked on file I/O is sensor data loading itself is intensive. That is, you load really large bytes of objects, and yeah. And another thing is the sensor data is loaded after the fact that the parquet is loaded, and so you have multiple workers that are trying to load individual data artifacts within a single training job, and they all sort of route through the metadata store to get the address of the individual sensor data artifacts. So what that does is you create multiple calls. You have multiple calls to the metadata store, and that thrashes the metadata store, because these training jobs can have hundreds of workers, and you have many training jobs sort of all going at the same time. So the solution to this is actually pretty simple. You just zip up all the individual sensor data artifacts into a single archive, and you cache the address of the archive, so that any subsequent sensor data artifact lookup, you wouldn't have to worry about it, because you would already have the address of the archive. That had a phenomenal impact on the data loading speed. So we observed like a 2x nominal speedup and up to a 5x speedup when the metadata store was congested. One other thing that could be done is actually loading less data. While it sounds easy, it's not that straightforward. But even before that, some context over here, generating these network inputs and targets is compute intensive, and the resulting transformed artifacts are much smaller than the initial raw sensor data that is read. So the solution to this is actually moving all the deterministic transforms upstream, and then materializing the output of these transforms as versioned artifacts. So then you load these versioned artifacts during actual training run, so that reduces any I/O bottlenecks. We also allow falling back to the full pipeline, so that your ML developers can experiment with different parameters. But yeah, that's most of our training jobs actually just rely on the processed data pipeline. The outcomes with that was there is a strong reduction in both memory and compute usage per actor, so, and at the same time file I/O as well. So there's a 66% reduction in file I/O and actor memory usage, and a lower compute requirement per actor. That again allows for a strong increase in concurrency, thereby making the data pipeline even more performant. So something that actually affects both the data pipeline and the training step is serialization. So some context over here, developers actually prefer working with data classes within MapBatch's UDFs, and they will often have like non-array metadata types. While array data expects you to work with NumPy array decks, because numpy array dex could be can be zero copy transfer. So there's a fundamental mismatch over here with developer expectations or developer preferences and data requirements. One other thing to note is when you're working with multimodal sensor data, you can often have inconsistent shapes per sample, and that automatically breaks array data's batching requirements because it enforces this requirement of all data samples having the same array shapes. So the serialization solution that we came up with was as follows. What we do is we extract array-like attributes into numpy arrays, and then we set some guardrails around shapes so that users wouldn't do the wrong thing with their arrays. Then we serialize the remaining data class fields into bytes and prepare this dictionary of numpy arrays that could be transferred over to the training node. On the training node, this dictionary of arrays is unpacked into a batch data class and forwarded to the model forward backward pass. So that actually solves like a lot of problems. And what we saw was that allowed developers to use data classes without any issues, and they were also able to add any non-array metadata types without running into serialization issues. And because there are proper guardrails that are set up, they wouldn't have to worry about inconsistent shapes during actual training runs. Lastly, some more additional optimizations to call out. First is setting the right data types. So within the data pipeline, it is imperative to set the correct data types for all the variables that are instantiated, because that reduces memory utilization and any network egress and ingress costs that are incurred while transferring these larger variables. A tip on array data tuning. So one of the things that we observed was array schedules 4 tasks per actor, but it doesn't appear to divide blocks evenly. So setting the right number of partitions, for example, when you're using from items, to something that is greater than 4 times the number of CPU requirements fixes that issue. And that ensures that there is an even distribution of workload across actors, and you achieve like a desired concurrency that might not happen if this is not done. Lastly, a tip on observability. We recorded the array data progress bars and logged them over multiple experiment runs. And we preferred that over Grafana and Prometheus because it was just easier to track progress during all of this optimization journey. So with that, we reach the key takeaways, and here are the key takeaways for you guys. We enjoy working with array data. It enables rapid iteration compared to a PyTorch DataLoader. It has a lot more tunable options, and it provides better observability compared to a PyTorch DataLoader. And it enables you to add more CPU nodes into the mix when you need that additional training boost. That's not possible with a PyTorch DataLoader. And lastly, you avoid any gotchas that are associated with sharding data, where, as Richard was previously mentioning, we were observing some rank stall because they were starved of data. That just doesn't happen with array data loader. And the final comparison table, compared to the Torch data loader, you can see that the optimized version actually reduces the GPU usage by half. And the CPUs remain the same because there is an additional CPU node that is added. But the speed boost that we get is of the order of 9 times. And compared to the initial array data version, we reduced GPU usage by half and CPU usage by up to 4 times. And we get a speed boost of 3 times. Yeah, that's it. Thank you all for coming, and we are open to any questions that you have.
If there are any questions, I can pass the mic.
this time series data, or I mean, sensor data often has that notion of time, and you have to perform time alignment, that sort of thing. How did you kind of approach that? Because I think that some of this seems, like it might apply very broadly beyond just sort of sensor orientation and these very like time-based indexing kind of things. How did you all kind of approach that problem when you have to load a correct sequence of rows in order to not have lots of small fetches and that sort of thing?
Usually the way we structure like sensor data, as we mentioned, like we just zip them all up in an archive. And so that can usually last, like we zip them up for a specific time unit. And so we don't have to worry about small reads.
Yeah, so I was wondering, as you were optimizing these data-intensive workloads, did you need to use any different processes for different teams who may have had highly different pipelines for things like, let's say, different data modalities, different sizes, file types, like time, including things like time series data? Did you have to tailor your process towards these individual workflows?
I think so. Yeah, it just depends on the team. Like you said, some teams do have these heavy sensor data objects, while some teams didn't. So the optimizations that we had built for, they actually apply to any teams that say work with images or point clouds. And yeah, usually that is you have a time element involved over there because you would record it over a period of time. Yeah, but I don't know if that answers your question, but yeah, most of the optimizations, they apply to any heavy sensor data artifacts.
There was also a bit of a learning curve for teams. Our previous approach was, I think, easier to customize, and folks were a lot more familiar with it. Ray data was certainly new to the team, and it definitely took some effort to get the team to adopt it and also be more familiar with the patterns that work well for Ray. So there was definitely some education required there.
So I have two questions. Like, first of all, for the data processing before Ray, you might have something else, right? Spark or something. How did you transition here? Because I see the pattern where most people trying to use Spark for data processing existing one and then calling Ray and all this. I see hybrid systems everywhere. So how you transition? That is a one question. And second is that you say that precision, right? The setting the precision to save the data. Is it in the model or is it in data frame?
Yeah, so I guess the first question, we aren't using Spark. We're actually using Ray for everything. We use Ray to do all of our pre-processing and data set generation ahead of time. Do you want to answer the question in terms of precision?
Sorry, I didn't get the second question. Could you go again? Precision?
So you mentioned that you tune that precisions, right? The numbers precisions for int and or float, right? So question is it like a model setting or is it like while loading the data when that comes in picture?
Anywhere in the data pipeline. So it can be within the training step. So as you're saying, setting the right data type, it happens both in the data pipeline and the training step. Usually ML developers focus more on the training step because that's where majority of their time usually goes in. And so they can forget setting like the right data types within the data pipeline.
I think it's also a bigger issue with Ray, because with Ray you have to remember you're transferring the data between instances, whereas with the Torch DataLoader it's all on the same machine, and so there's less of a cost of transferring it.
How does your data team support like diverse data query patterns and use cases? Like say, for example, SQL-based metadata queries, time series queries, maybe embedding-based similarity search, full text searches. How do you structure the canonical data format, the files to support all these diverse workload for training by different teams?
Yeah, I think that's a great question. And there's a lot of work behind that. I think there's a bunch of different use cases, and it's kind of difficult to put together one solution that works for everything. I guess the philosophy that we have is we try to produce what we call a unified data set or a universal data set, which is kind of processed enough that it's close to what people need, but they can still use it for multiple different applications. And then we provide access to it in different ways, by indexing it, et cetera.
We have time for one more question, and I saw a few more hands. So if you still have questions, you can catch Richard and Krishna right outside in hallway after this one.
Hi, I saw that you were using collate function in one of the slides you had before, and we are also using that for a robust batching implementation for our training. I was wondering if it was something that you guys are doing and that you guys realized you had to do in the beginning, or what steps eventually got you to lead to the decision to use something that overrode the initial batching implementation?
It was mostly through profiling. When we looked at profiling the training step, we realized that there was a lot of CPU time spent concatenating arrow arrays, and that led to the hypothesis that if we could remove that, we could speed up training, and that panned out. I guess my understanding, talking to any scale folks, is that the recent versions of Ray supposedly have improved this. We haven't tried that out, but it's something on our to-do list. So maybe something to look into.
Thank you, Richard and Krishna.
Thank you.